And the very last one we're going to have a crack at in this course. So, second order differential equation with a sign in it in this case. So we just start off by doing what we did before. So we're going to try and find the complementary function, which means we start with the auxiliary equation. So m squared plus 3m plus 2 equals 0. And again, this thing factors quite nicely to m plus 2, m plus 1 equals 0. So it implies that m equals -1 or -2, and so here again we have real and different roots, so we're in this situation. So the complementary function this time is going to be of this form. So the complementary function is x equals ae to the minus t plus be to the minus 2t. Okay, noticing now that I'm using x's and t's, as this was dx dt rather than y's and x's in the previous example, but no problem. So there's my complementary function, and before I try and work out what a and b are, I need to work into the particular integral. So looking at the particular integral, so for the particular integral, the first thing to do is to look at the list of types of particular integral with and decide which one of these we're looking at. And in this case, it's 3 sine t. So it's this one here. Our function at the end is 3 sine t. So k is equal to 3, and f of x is just t, or the function is just the variable. So we're going to end up with c lots of cos t plus d lots of sine t. So the particular integral in this case is x equals c lots of cos t plus d lots of sine t. Okay, and now we start the fun bits, because I want to be able to substitute this back into this equation. So I've got something for x, but I need the first derivative and the second derivative. So x dash is negative c sine t plus d cos t, and the second derivative of that will be negative c cos t minus d sine t. Okay, and now we can stick those into the equation. So what have we got? We've got, just copying down the original equation, x double dash plus 3 lots of x dash plus 2 lots of x equals 3 sine t, implies that, making the substitution. So x double dash is minus c cos t minus d sine t plus 3 lots of this one, so minus 3 lots of c sine t plus 3 lots of d cos t plus 2 lots of the top one, 2c cos t plus 2d sine t, all equals 3 sine t. Right, okay, now that's pretty straightforward to solve, because all we've got to do is equate the sines and the cosines. So in terms of cosines, we've got negative c cosines, so that's a cosine, plus 3d cosines, plus 2c cosines. So we've got minus c plus 2c is c, and then we've got plus 3d. So c plus 3d equals cosines on this side, none at all. And looking at the sines, we have minus d minus 3c plus 2d, so minus d plus 2d is d. And then we have, in terms of the c's, we have just minus 3c. So probably better to write it the other way around, don't I? So minus 3c plus d equals 0. Oh, no, it doesn't equal 0, it equals 3, doesn't it, on a roll here. So let me just write those again. So the top one is that, and the bottom one, minus 3c plus d equals 3. That's more like it. Okay, so now we have a simple system of simultaneous equations. So if I multiply that top one by 3, I get 3c plus 9d equals 0. On the bottom, minus 3c plus d equals 3. Add those, gives me 10d equals 3, which implies that d equals 3/10, which means that c must equal, if that's 3/10, that's 2.7 divided by 3 is negative 0.9. Okay, so there are my values for c and d. So in this case, the particular integral is equal to, looking back up to where I wrote the particular integral, is x equals c lots of cos t plus d lots of sine t, just taking this particular integral and substituting into c and d. Okay, so I now have a particular integral and I have a complementary function. So the general solution is just the summation of those two things, is x equals, from the top there, a equals e to the minus t plus b e to the minus 2t plus my particular integral, which is minus 0.9 cos t plus 0.3 sine t. Right, whew, got there. So now I've actually got a general solution, and if I go right back up to the top, I have to apply the initial conditions that when t equals 0, x equals negative 0.9, and dx by dt equals negative 0.7. So I'm going to have to do a derivative. So let's do that before I do anything too silly. So I'm going to need this derivative, which will be minus a e to the minus t minus 2be to the minus 2t, and if I differentiate this thing, I'm going to end up with plus 0.9 sine t minus 0.3 cos t. No, I tell a big lie, that'll be a plus, won't it? Because when I differentiate the sign, I get a positive cos. It doesn't change the sign. Okay, so I now have a expression for x and for x dash that I can apply my particular solutions to. So at t equals 0, what do we know? Well, we know at t equals 0 that x equals negative 0.9. So looking at this top equation, negative 0.9 equals. Okay, this is the point where t equals 0, so that bit goes to 1. That bit goes to 1. T equals 0, well, the cosine of 0 is 1. And the sine of 0 is 0, so that bit disappears. And also at t equals 0, we know that, going back up to the top, the first derivative is negative 0.7. So we can make this equation work as well. So negative 0.7 equals, okay, so same thing, t is equal to 0, t is equal to 0, t is equal to 0, so it goes to 0, t is equal to 0, that one goes to 1, so we end up with 0.3, and we can try and solve these any ways we like. It's just simultaneous equations, so if I just add those two equations together, because the a's will disappear, so I end up with negative 1.6 equals no a's, negative b, negative 0.6. So what have I got? If I add that onto that side, I'm going to end up with negative 1 equals negative b, which implies that b equals 1. And if b equals 1, a had better equal. If b equals 1, that's going to give me 0.1. Take off that side, negative 1. So the general solution for the last equation in the course is x equals, so going back to my general solution here and just substituting in a and b. So a is negative 1, so minus e to the minus t, plus b is just 1, e to the minus 2t, minus 0.9 cos t, plus 0.3 sine t. And that is the solution to the differential equation that we started off with these initial conditions. Okay, if you want to check that out, you could just take the general solution down the bottom of the page there and differentiate it twice and differentiate it once and bung into this equation and convince yourself that it works. So again, the process is kind of long, but it's not too bad. So you start with the auxiliary equation to find the complementary function. You pick the particular integral off the sheet based on what the function is going to be. You have to differentiate it a couple of times so you can stick it back into the original equation. A little bit of algebra to work out the variables. And once you've got the particular equation, then you join it with the complementary function to form the general solution. Differentiate that once so you can apply your boundary conditions, which in this case were a straight one and a derivative one. And then again a little bit of algebra to work out what the constants of integration were, and then stick it all together for the final general solution.